Okay, am I audible? Very good. I think let's get started. Welcome everyone to lecture 21. Today we actually have an ambitious plan. We have 3 sub-lectures. I will first finish multiprocessor, the lecture that we have started actually last week. And then we're going to get to 2 important issues regarding multiprocessors, especially when we want to have it like a tight multiprocessor design using shared memory paradigm. Then we get to this consistency, memory consistency issues, and also cache coherence, which we're going to see today. Any question? Okay, very good. So these are some readings that we also mentioned last week. You can also check them. And also for memory consistency and cache coherence that we're going to see today. So remember that in multiprocessor, we actually have 2 types, loosely coupled multiprocessor and tightly coupled multiprocessor. And essentially with loosely coupled, there is no shared global memory address space. And it has been actually implemented a lot in multi-computer network when we have different computers and they are connected through a network. Usually for those communications happening through message passing. But in our computer systems, when we have multiprocessors, we are using this tightly coupled system, which we essentially have a shared global memory address space, which is going to be used in order to synchronize across different applications and different threads that they are running. So we were discussing about limitations of parallel speedup. Remember about this example that we tried to work on it last week. And essentially, we talk about first, some performance for the sequential execution and also for the parallel. And then at some point, say that, okay, for the single processor, we need to look into better implementation, better algorithms, so be fair. So all of these actually are just a recall for you for last week. And then we were discussing about superlinear speedup, that usually when we have in parallel programming, when we are using P processor, at most, we are expecting to see a speed of a P, but that may not usually happen because of other problems like for example, sequential bottleneck of the process of the application that we don't usually we are observing sublinear performance. But in some cases, actually, people are reporting superlinear performance, and we discussed that one reason could be because of unfair comparison. That essentially we are not comparing against the best serial algorithm. But another effect would be also cache and memory effects. So essentially, when you are increasing the number of processor, you are actually collectively also increasing caches and also memory. So at some point, because of larger cache spaces and also larger memory, you're gonna get you might get superlinear performance, but it's not because of the parallelism that you're getting. It's actually because of the larger memory spaces. So all of it was just a recall for you. Any questions for this part? Okay. So now let's get to some metrics which are important for, they're somewhat important, especially in the past when we wanted to, evaluate the performance of parallel applications. So these are traditional metrics, like assume all P processors are tied up for parallel computation. One metric is utilization, how much processing capability is used. Usually the way we calculate is the number of operations in parallel version divided by processors times time. So that's the utilization metric. Another metric is redundancy, how much extra work is done with parallel processing. So then for redundancy is like number of operations in parallel version divided by number of operations in best single processor algorithm version. So when you go to the parallel version, you might do some more instructions. We just want to see that, okay, how much we are doing more. So that's a redundancy metric. And another metric, which is efficiency, which is usually is calculated by time with one processor divided by processor times time with P processors. So here, like the processor is the number of processors, and this is the time which is time takes when you are executing these parallel applications. So this division actually gives you the efficiency. if you are careful with the, essentially with the dimension of this metric, you can see that people try to estimate actually efficiency by this metric, utilization divided by redundancy. So that gives you efficiency. Specifically in this case that we consider that the time takes to execute each operation is actually 1. So, so in that sense is actually U divided by R. So we can actually do this for our prior example. So if you remember the parallel implementation of this, if I just quickly go back to that slide. Yeah. So this is the parallel operation. So in cycle 1, we actually have 3 operands, 3 operations. In cycle 2, we are also doing 3 operations. So if you just, fill up this table, that so we have P processors. Here is 3, and it's also the time. So in the cycle 1, we have 3 processors active. At cycle 2, we also have 3 processors. At cycle 3, we have only 2, and cycle 4 and 5, we have only 1. So now the number of operations is actually 10, and we actually have 3 processors at most, and the number of cycles is 5. So 10 divided by 3 times 5 is 10 over 15 is going to be utilization of this multiprocessor design for that specific application. And redundancy is actually how much extra work due to multiprocessing. So operations with basically parallel, the best parallel algorithm is 10, and operations with the sequential algorithm, the best is 8. So redundancy is 10 over 8, which is, you can some number. So the important thing is that redundancy should always be greater than 1, equal to greater than 1. So if you remember the poor implementation for the sequential algorithm, it was actually 11. So basically it was, if you want to calculate redundancy, it's going to be 10 over 11, which redundancy is lower than 1. So if you get the redundancy lower than 1, that should immediately ring the bells, that something's wrong here. And for efficiency, essentially, you need to divide U by R, and then you get this 8 over 15. Question? Okay, these are quite actually simple. They are good for exam questions, but just some calculation. So Amdahl's law and some caveats of parallelism. So I think you remember Amdahl's law that essentially the speed up that we are getting for a parallel application is limited by the serial portion of the application. So this is one way of representing Amdahl's law, which speed up is 1 over 1 minus F. F is actually the parallelizable fraction of a program. So 1 minus F is going to be the sequential portion of the application. And F over N, which means that the parallel portion you can perfectly parallelize across N processors. So that's the Amdahl's law. And we can see that the maximum speed up limited by the serial portion, which we call it serial bottleneck. So in reality, actually, we are getting sublinear performance improvement when we are, or speed up when we increase the number of processor. And that's kind of because of the Amdahl's law. So, for example, if you have 90% of your application parallelizable, then at most you can get, you can get 10 speed up. So if you increase so if you get back to this formula, if you increase the n to the infinity, it's going to be 0 here, right? So F over N is going to be 0, meaning that the parallel portion is going to be 0. I perfectly parallelize it. So then it's going to be the speed up at most is going to be 1 divided by 1 minus F. So that's the limit we're going to get that. So essentially, if the parallelizable portion is 0.9, then at most you are getting 10 speed up. If 0.98 is going to get to higher speed up essentially. So that's a limit that you can think of. So it's also another way of showing that as you increase the so the speed up that you're getting as you're increasing the parallelizable portion of the application essentially with different number of processors. I think we also have some Excel results, but maybe later. Okay. So that's the serial bottleneck. But unfortunately, parallel portion is also usually not perfectly parallel. We discussed it actually in our memory controller lecture. We were discussing about how we can handle multi-program and multi-threaded requests that they are going to the memory controller, how we can basically schedule requests that are coming from different threads, and these threads are actually related to one application. So we discussed about different essentially overhead is happening for the parallel portion, which is one of them is synchronization overhead. Another one was load imbalance overhead, and also resource sharing overhead. So this is actually another picture for that sequential bottleneck. As you can see, as we increase the parallel fraction, how much speed up we can expect. Like with, as we get to the closer to the one, like we can parallelize more and more, the speed up is going to be much more, and then you can actually improve more. So that's very fundamental. Essentially, many of these applications you cannot avoid, you cannot get away from that serial portion. Because in the end, there might be, so when you want to make the work parallel, there should be some portion of the application just to prepare the work for the parallel part of the application, and then spawn threads. So that part is serial, or can be also partially parallel, but it's not fully parallelizable. So then as you increase also the number of threads, and then you want to parallelize the parallel portion more and more, then that serial portion actually also needs to work more, because you need to spawn more threads essentially. So in the end, you're going to be bottlenecked by that serial portion, which you cannot get more performance improvement. Is actually what I'm trying to say, that the main cause is actually non-parallelizable operation data. And essentially, there are other also causes that single thread prepares data and spawns parallel tasks, which is usually sequential. But there are also other examples of sequential bottleneck, which is actually happening in the parallel portion of the application. Like, for example, we have some critical sections that we are basically protecting with locks. So these critical sections are going to be sequential. I'm going actually over these slides quite fast because we already discussed them actually in the past. When we have different threads in different critical sections, then thread one here is getting idle because it cannot get enter the critical section. So we also discussed about load imbalance and also resource contention in the previous lectures. So in synchronization, the problem is that, so you're using locks, mutual exclusion, barrier synchronization, whatever synchronization primitive that you're using. And then there is this communication that tasks may need values from each other. So that's the reason that you're doing synchronization. So this synchronization would cause thread serialization when shared data is contended. Essentially, when you have synchronization, these threads, they need to wait for each other. You are kind of serializing execution of those threads. So you're not parallel in that sense anymore. And load imbalance is also very important because when you want to partition your work across different threads, you in the end, you might get some threads that they have less work to do, and some threads that they have more work to do. And those threads that they have less work to do, they will finish the execution faster, and they need to wait for other threads, because at some point you have a barrier that you want to synchronize all together and then continue. There are solutions to that. Also, people are looking at dynamic partitioning, as well as also some kind of partitioning task that you just put the task in a queue, and different threads are gonna fetch the task from that queue and execute. And when one thread is done with the task, it's gonna get another task from the queue. So there is a queue which is kind of centralized, but that queue also can be contended again and cause some issue here. And resource contention, I think you can also guess. When, for example, for memory, like we have a shared memory channel, is gonna be contended when we have different essentially threads. Yeah, so we discussed about these issues in the past as well. So that's why I'm actually going over them quickly. Critical section, we discussed it. And also critical, in one example in MySQL, you can see that there is this open database table, which is we access basically open table cache, which is critical section. But then perform the operations is going to be parallel. So the speed up that we are getting from this MySQL when we increase the number of cores is something like that. So in the end, at some point, your performance is getting saturated, but then at some point you may get actually lower performance because you are actually paying a lot more because of the contention, and that is not helpful anymore. So there are some interesting works that people try to accelerate the sequential bottleneck of application by scheduling on large cores, essentially. So our many core system, or let's say our SoCs nowadays, they include both small cores and large cores. So small cores are very good for parallel portion of the application because you can have many of them, but each is actually not very powerful. But in that SoC, you can also have some large cores, which you don't have many of them, but each one is actually quite powerful. And if you can actually schedule the serial portion of the application, or whenever you are on a sequential bottleneck, essentially, you schedule on that basically large core, then you can potentially reduce the overhead of sequential bottleneck and get performance improvement. So with such techniques, for example, we can get to, this kind of a curve that, we can continue getting better performance, which is called asymmetric multi-core design. So this, the black curve is actually showing symmetric multi-core design, that all cores are the same and potentially they are small cores. But in asymmetric design, you can have a lot of small cores and also a few large cores, which in large cores, you can actually accelerate the sequential bottleneck. Unfortunately, this semester, we don't have time to have a lecture on bottleneck acceleration. I have some links for that lecture in the past, which you can also check as a kind of optional. But we will also premiere some optional lectures after after holidays at some point. But yeah, basically this part is for you. Just if you are interested, you can check more. And we are not going to have it in this semester. Okay, for barriers also, like again, with barrier also, you can use that technique in order to accelerate the sequential bottleneck. But I think you remember the issue about barriers, which I already also discussed, is actually coming because of the fact of imperfect load imbalance across different threads. Then some threads are going to finish the job quickly or faster, and they need to wait or be idle until they get to the barrier. We also discussed about the stages of a pipeline programs in the previous lectures. And if you remember this picture, that essentially core A gets some input from this queue and then generates some output to another queue, which this queue is going to be used as input for core 2. And also core 2 will generate inputs for core C, and then C is going to use that. So if these are not going well, then essentially some of these cores is going to be idle, and they are not. So maybe they don't have enough, they don't have fresh data in the input queue to fetch and execute. And or maybe the other way around. So they can get inputs, but the output queue is still full because another stage is not fast enough to evict the data from that queue. So when this queue is also full, when the output queue is also full, then that core cannot continue and put more data to that queue, and that can cause some serialization or waiting, essentially. Okay. So essentially, parallel programming is quite difficult. So there is little difficulty if parallelism is natural, like when we have embarrassingly parallel applications. Think about like matrix multiplication. For these things, our application is embarrassingly parallel, and we can easily essentially parallelize it. Multimedia, physical simulation, graphics, large web servers, databases, and so on and so forth. But difficulty is in getting parallel programs to work correctly and optimizing performance in the presence of bottlenecks. So essentially, there are many applications that how to parallelize them is not very easy to understand, to reason. How to effectively partition the work across different threads is not also easy. And there are a lot of bottlenecks which might happen. And in the end, a lot of parallel computer architecture is about designing machines that overcome the sequential and parallel bottlenecks to achieve higher performance and efficiency, and making programmers' job easier in writing correct and high performance parallel programs, which both of them are actually very important. And I think for the second item, actually, we've been trying a lot to make the life easier for the programmer, but still, I think writing a parallel application is not easy for programmers. So the thing is that if you want to make it easier and easier, then the hardware is getting much more complicated, and at some point you need to leave some of the performance improvement that you could have in the hardware in order to make sure that you are making the life for programmer easy. So at some point there is a trade-off, how much we want to get better performance. Like think about out-of-order execution, all these caching, these all can complicate the problem, which we're going to see a lot more today. Okay, question? So just some of these papers, like that I also mentioned about, how to accelerate critical sections. This work is, for example, one of them that use this asymmetric multi-core design in order to accelerate sequential bottleneck. And another work, bottleneck identification and scheduling. So we try to understand which portion of the application is a bottleneck, and then we schedule that bottleneck on a large core in order to accelerate performance. Yeah, unfortunately, as I said, this semester we don't have time to go over these works, but you can check them in prior incarnations of these lectures. And utility-based acceleration is also similar to this kind of work, but we are defining a metric, which is utility, which is that metric is actually very general and accurate to such that we can understand which part is actually the bottleneck of the application. So the thing is that you understand that this portion of the application is bottleneck, but when you want to move that, migrate that part to a large core to execute, then you are paying some overhead for that, right? So then this actually utility-based acceleration comes to play here. Essentially, you need to, every time you want to do that, you need to calculate this utility and see that if I migrate that execution to the large core, am I getting better performance or not? Because you need to also pay the overhead for that movement as well. So once you know that, and then your utility, you get a good result for that utility, essentially, then you can accelerate, then you can schedule to the large core and accelerate that application. Okay, and also another work related to how you map data across these applications, across these cores, not application, across these cores. Data marshalling is actually very interesting work, which unfortunately we don't have time. So you can check these works. Here, actually, that's what I was talking about. So in this structure, you can see a homogeneous design, or let's say symmetric, that we have several small cores, right? But then you can also have no, A is not accelerated, is asymmetric. Asymmetric chip multiprocessor, which, for example, you have one here, for example, you have one large core, and other cores are small. So once you have that, you have this potential to essentially schedule the sequential bottleneck to the large core to get better performance. And here also another picture for bottleneck acceleration, that's essentially for small cores, when they have some bottlenecks, they can schedule that to the large core. And in the large core, essentially, we have some table, some queue that we store, like this bottleneck ID, and also how much we are waiting for that bottleneck. And based on that, we can schedule for the execution on the large core. Okay, any question? So now I think we need to go to lecture 21B. Let's see if I can do it. Is it open already? I think it's not open, no? 21B. Okay, so sorry. If you can also get to the all good. Thank you so much. Okay, question. Was that fast? Yeah, but the topic, I think you were aware of that. You've seen this, essentially this sequential bottleneck in other lectures as well. But this lecture, memory ordering, is going to be a bit slower, I think. This is a kind of newer topic. Okay, so remember about this difficulty in parallel programming, which essentially we just discussed it, that we need to design machines that overcome the sequential and parallel bottlenecks to achieve higher performance and efficiency, and also making a programmer's job easier in writing correct and high performance parallel programs. So we don't want to go into a lot of detail here, but essentially there is a trade-off between performance and correctness. So these are two metrics that are fundamentally at odds with each other. We can always improve performance at the expense of correctness. We can, for example, forget some critical lock in our program and hope that that's going to be correct. We can design architecture that are ignoring ordering of operations. We're going to also see some example, because there are also some works that they try to use this paradigm in a speculation manner. They say that speculatively, I'm going to think that I have the lock and I'm allowed to enter, for example, the critical section. So basically, they speculatively do the execution. But at some point, if you realize that that was wrong, they are able to roll back and repeat that. So there are also papers in that line, which I'm going to mention one of them. But you've seen that also in the past, using this trade-off, for example, in this work, Eden, that we discussed it, and also this heterogeneous reliability memory, when we have, when the memory is unreliable. So you can make the memory unreliable in a sense that in some portion of that, you're reducing reliability, but you're getting better performance and energy. So for your application, if that application can tolerate errors, then you can intelligently map the application on different portions of that memory and get better performance. So sometimes actually people can play with this trade-off actually nicely when the application allows that, essentially. So yeah, you can, I think you remember Eden paper and also heterogeneous reliability memory. And also this lecture on latency reliability trade-off from the past. But so performance versus correctness is also very similar to the latency reliability trade-off. And essentially reliability is at the hardware component level, but correctness is at the program semantic level or hardware function level. And also we have seen examples of latency reliability trade-off before, like in the lecture of memory latency and also low latency memory. We even use that for generating puffs, for example, also. Sometimes you make your DRAM unreliable just to get puffs, for example. And also sometimes you want to generate random numbers, for example, you can use that. But yeah, these are from the past that we discussed. So don't forget that we can also sometimes intelligently play with this trade-off between latency and performance, and essentially correctness and reliability of the system. But now I want to jump into memory ordering in multiprocessors. So these are some reading, which the first one is required and others are recommended, so you can check them. So I will first distinguish between memory consistency and cache coherence. Actually, cache coherence in the past, some people also call it cache consistency. But memory consistency, people never call it memory coherence. It's a kind of unfortunate naming, you know, that people think that why this is memory consistency, that one is cache coherence. But essentially in cache coherence also, we want to be consistent across different caches. But the main difference is coming from the fact that consistency is about ordering of all memory operations from different processors to different memory locations. So all memory operation which is happening in a multiprocessor, we want to have a consistent view across different processors essentially. So that's the consistency that we are talking about and that's talking about global ordering of accesses to all memory locations. However, coherence is about ordering of operations from the cache coherence. It's about ordering of operations from different processors to the same memory location. So we are actually kind of thinking about local ordering. So local ordering of access to each cache block, for example. So that's the cache coherence problem. So these two are fundamentally different, but they are also not completely unrelated. So you're going to see that there are works, we're not going to discuss them a lot, but there are works that, for example, the consistency model is when they want to implement it, they actually get also benefit from the coherence protocol. And also other way around. Sometimes coherence protocol is implemented or is relying on some consistency model that we have in our system. But fundamentally, they are talking about different things because consistency is talking about the global ordering of all accesses, but coherency is talking about local ordering of accesses. So for example, for consistency, we are talking about different memory locations, like A, B, C, D, E, F, G. So all these are different memory addresses. But in coherence, we are talking about one cache block, for example. So we want to see all the requests to cache block A. We want to have a consistent view across all different cores. Make sense? Okay. So yeah, so that's it. Remember about difficulties of multiprocessing. So when we are talking about the ordering operations, that we have these operations A, B, C, D. In what order should the hardware execute and report the results of these operations? So there is a contract between programmer and microarchitecture, which is specified by the ISA. And with that, we can preserving an expected or more accurately agreed upon order simplifies programmer's life. The thing is that if you have an agreement, then we have ease of debugging. So if you don't know what's going on, which order is going to happen, so you run the application and you get some error. Then you repeat the application in order to debug it, and then some other order happen, and then you may not see the error anymore. So there is very hard for parallel application. One is that sometimes it's actually very hard to debug. Actually, always is very hard to debug, and it's also potentially coming from the fact of this ordering of the operations, because some errors may happen because some specific ordering, which might happen. And also how we can recover from some state, like ease of state recovery, and also like exception handling. Sometimes you have exception and you want to recover from the exception. So you should know there's having precise exception if you know that topic in the basic computer architecture. That's very much needed to have a agreed open protocol between the programmer and also the hardware, between the ISA and also the hardware. However, preserving an expected order usually makes the hardware designer's life difficult. And we're going to see that in the end, we don't get a lot to the expected order. So just to make sure that the hardware design is practical and we don't want to sacrifice performance a lot as well. At some point, if you want to make it very expected, then you need to sacrifice the performance in hardware, which is not going to be desirable. Okay. Yeah, so yeah, as I said, especially if the goal is to design a high-performance processor, recall load store queues in out-of-order execution and their complexity. Okay. So memory ordering in a single processor, we have this with von Neumann model. So we have this sequential order. Hardware executes the load and store operations in the order specified by the sequential program. We also have out-of-order execution, but in out-of-order execution, that also does not change the semantics. Hardware retires or commits essentially the instructions and also the load and stored operations in the order specified by the sequential program. So you're not changing that part. So which is very important. So this provides at least two advantages. One is architectural state is precise within an exception. So whenever you have an exception, you know how to recover from that exception. And also architectural state is consistent across different runs of the program, which makes the debugging easy. So for single processor design, actually is easy to debug. I mean, debugging is always hard, but at least here is easier to do because you can reason about all the operations and also the ordering which is happening. But has disadvantages that which is preserving order adds overhead and reduce performance, increases complexity and reduces scalability. So if you know the other way of paradigm, which is, for example, data flow processor, a memory operation executes when its operands are ready. So ordering is specified only by data dependencies. And with that, two operations can be executed and retired in any order if they have no dependency. And that's make their life hard for the programmer. So of course, the good thing is that we have lots of parallelism, and there is no this control flow dependence, for example, with data flow processor. But at the same time, you have only data dependency, because that's the only dependency that would limit the parallel execution of that application. But of course, there is no precise state or ordering semantics, and then actually it's very hard to debug, and also order can change across runs of the same program. Again, very hard to debug. Make sense? However, memory ordering in a MIMD processor, multi-instruction, multiple data, and that's actually what we want to talk about it. Because in SISD, memory ordering is not a problem, because von Neumann model is, make sure that your all memory requests are ordered. But in MIMD processor, each processor's memory operation are in sequential order. With respect to the thread running on that processor, meaning that each processor actually obeys von Neumann model. So that's for sure. In MIMD system, we are assuming that each processor actually follows a von Neumann model. But multiple processor executes memory operations concurrently. So now the question is that how does the memory see the order of operations from all processors? Or in other words, what is the ordering of operations across different processors? Is it going to be different from different processors, the order that they are observing or not? So why does this even matter? As I said, ease of debugging, correctness, and also performance and overhead. So at some point, if you want to make sure that this memory ordering is actually very fixed, then you get to some performance limitation and performance overhead. But at the same time, ease of debugging is also very important, such that the programmer can reason about the order of the operations, and of course, for correctness of the application. So essentially, we're going to discuss a lot about correctness in this lecture, but ease of debugging is kind of thing that you should not also forget about it. Like, there are also a lot of works in that line. Like there are some works in literature that people try to do record and replay. So when they run a parallel application, they're going to record the order of execution and then replay based on that order. And this record and replay can be implemented as software and also in the hardware. So there are works that people, for example, suggest that we have some units in the hardware such that they can accelerate this record and replay, which is very important for debugging, essentially. But today we're going to focus a lot on correctness. Make sense? Okay. So when we are protecting shared data, essentially, then this order is important. So how we protect shared data? Threads are not allowed to update shared data concurrently. So we are going to use some essentially critical sections. So accesses to shared data are handled by critical sections, or some synchronization constructs like logs, semaphores, condition variable, and so on and so forth. So only one thread can execute a critical section at a given time, which we have this mutual exclusion principle. So a multiprocessor should provide the correct execution of synchronization primitives to enable the programmer to protect shared data, essentially. So we have these synchronization variables and constructs, and programmers are relying on them to write a good or correct program. But if the hardware is not protecting that, then the code which might actually work at the software, when you think about the logic, is not going to work in that hardware. So that's the topic that we want to discuss about it now. So we're going to see an example with this Dekker's algorithm. We are actually assuming here that programmers actually has done a good job, to make the code correct. But we should also don't forget that that actually is an important topic to begin with. And also you can check these readings from Dijkstra and also Dekker's algorithm for mutual exclusion. But we're going to see an example very soon that assuming a code is correct using Dekker's algorithm, if the hardware is not handling this consistency well, we're going to see that we might have a problem or not. Okay. So yeah, here is an example. When you want to protect shared data, we have these two processors, P1 and P2, and here also we have this critical section, right? So when the thread running on processor 1 wants to enter this critical section, it set the variable f1 to 1, and both variables f1 and f2 are initialized to 0. So here you set the f1 to 1, and then before entering critical section, you need to check if the f2, which is a variable for another processor, is it set or not? If not set, meaning that, okay, P2 is not in the critical section, so I can enter. And I enter, and when I'm done, we reset F1 such that we let the P2 to enter critical section when it wants, okay? So that's Dekker's algorithm, and it works. I mean, at the high level, you can see that this algorithm is correct. There are also a lot of optimization on this algorithm, which I'm not going through now, but all other also optimizations are also relying on hardwares. That hardware should obey, some semantics. Okay, now the question is that can the two processors be in the critical section at the same time, given that they both obey the von Neumann model? So assuming that P1 and P2 are using an interconnection network, are connected to the memory, and also memory is potentially banked. Okay. So the answer is yes, as you can imagine. Otherwise, we won't have this lecture. So here, as we can see in one example, that how this can happen. So when P1 wants to enter, so basically we have this. We set F1 to 1, and F1 to 1 complete from the processor 1's view. So in P1, actually, we set the value to 1, and then we just send this variable to the memory to be updated, right? So from P1's point of view, actually, A is done, and A is sent to the memory. And at the same time, in parallel, also P2 set F2 to 1 and send this, so we call it X here, just to make sure that we don't confuse them. This operation, this instruction, we call it X. So we execute the instruction X, and then this X sent to the memory, okay? So now at some point, actually the next cycle, P1 is gonna test the F2 value, right? Because we need to test if F2 is 0 or not, which means that we're going to send a read operation. So we have this load F2 sent to the memory. At the same time, P2 also needs to do that. So we send this load F1 to the memory. So now after some time, basically memory can service these loads actually before stores. Because we have interconnection network, and there are a lot of prioritization happening. Memory controller also may, prioritize reads over write. So in the end, it might happen that we receive the result for the load actually before than a store. So basically at cycle 50, we receive this P load F2 complete. So we get the value 0 because this update hasn't been done yet. And then at the same time, that one or another processor will also get this test value 0 because that the update to F1 has not been finalized yet. So then P1 is going to be in the critical section, P2 is going to be also in the critical section. And at some point at cycle 100, maybe we're going to be done with the stored operation, but that's too late, essentially. Make sense? Okay. So let's see what happened. We can examine each processor's view. So essentially, if you look at it, P1 sees that the order that sees is actually P1 first execute A, and then execute B, and then see also the X value that updates. So that's the order which processor P1 is seeing, okay? And P2 is observing that we first done X, and then Y, and then A, okay? So now you can see that in processor 1's view, A happens before X, and in the processor 2 view, X is happening before A. So now P1 and P2 don't have consistent view of the order of operations in the memory. And that's what's creating the problem here. So as long if you make sure that we might have different orders, but as long as P1 and P2 observe the same order, consistent order, then we're going to be good here at least, because Decker's algorithm would work at least. So that's the memory consistency problem that we are discussing. Any question? Yes. Cache consistency is actually cache coherence. You're talking about memory consistency. Yeah, but memory consistency is also, I mean, hardware needs to also support that. It's actually handled in the hardware. Yeah, yeah, of course. Yes, we're going to get to that actually. We're going to get to that. Why? So why is not fully supporting the hardware? That's your question. To make sure that the hardware is simple enough, and also we don't sacrifice performance. That's different. Cache coherence is for local, one cache. But here, if you want to make sure that all loaded store operations, you want to make sure the global order of all of them is fixed or consistent, then the overhead is much more. I mean, cache coherence is also expensive by itself. And not all applications, not all processors are actually supporting cache coherence. Like GPUs, for example, they don't. That's in the end a trade-off. How much you want to pay for the cost and also performance improvement. Okay, so the two processors did not see the same order of operations to memory, and the happened before relationship between multiple updates to memory was inconsistent between the two processors' point of view. And then each processor thought the other was not in the critical section, and both of them entered the critical section. So how can we solve the problem? We use this. One idea is to have sequential consistency, that all processors see the same order of operations to memory. There might be many different orders, but all processors are going to see the same order. So that's the sequential consistency topic. So if you want to learn more, learn about this sequential consistency, we're going to also explain. Is actually explained this paper by Lamport. So saying that a multiprocessor system is sequentially consistent if the results of any execution is the same as if the operations of all the processors were executed in some sequential order. So as long as you can come up with a sequential order for all, for all the instructions that have been executed, to show that, okay, this order is going to happen, then you're sequentially consistent. And that's one criteria. The second criteria is also that each individual processor needs to actually follow a von Neumann model. So each one needs to follow von Neumann model. And also whenever you have this execution in parallel, there should be a way to combine all these instructions to a sequential order and see that, okay, this can satisfy this ordering. Okay? So that's the Lamport essentially sequential consistency. So there's a memory ordering model or memory model, but which is specified by the ISA. How to implement that in the hardware is actually a big problem. That's why actually we don't have sequential consistent microarchitecture nowadays much, because this actually very basically costly to implement. And I would also sacrifice the performance a lot, because a lot of operations that we have in the hardware to improve the performance, like out of order execution, like caching, prefetching, all they actually may affect this sequential consistency. And if you want to be aware of that and design it, then at some point you're going to sacrifice the performance for that. So with sequential consistency, the program has an abstraction that memory acts as a switch that service one load or a store at a time from any processor. So all processors either currently service load or store at the same time. And each processor's operations are serviced in program order. So, okay. Then actually, so there can be actually potential correct global orders. So all is actually correct. You can actually work on it at home. So all these A, B, X, Y, I mean, these are the different orders of these operations which we discussed in our example in Decker's algorithm. So all these operations are possible. All these ordering are possible. But the important thing is that all cores or all processors are actually observing the same order. So which order, or actually they also call it interleaving, is observed, that depends on implementation and also dynamic latencies, because there are a lot of prioritization happening, which in the end you might see different orders. So even with this sequential consistency, which is actually so strong, we don't fix the order. And even with sequential consistency also, still debugging is a problem. Because you run and then you don't have fixed order, essentially. You have consistent view of orders, but then there might be many different orders, which you may see an error or not when you're debugging your application. Okay. So within the same execution, all processors see the same global order of operations to memory, so no correctness issue, and satisfies the happen before intuition. But across different execution, we might have different orders, which debugging is still difficult, as we discussed. So this paper for Lamport is going to be part of your reading as well, I guess, which you can check. So, but there are issues with sequential consistency. Any question? Okay. Yes. Yes. Yeah. So for loosely coupled processors, multiprocessor, you don't have shared memory address space. So essentially, yeah. So the problem is does not exist from the get-go. So whenever you want to communicate, you need to send messages. That's why message passing interface has been developed a lot. Yeah. Good question. Okay. So it's a kind of very nice abstraction for programming, but there are two issues. First is actually there is two conservative ordering requirements, and limits the aggressiveness of performance enhancement techniques, which we discussed as well. So now the question, critical question here is that, is the total global order requirements is too strong or not? Do we need a global order across all operations at all processors? How about a global order only across all stores? Because stores are kind of important in a sense that they are changing values. So maybe we should make sure that we have a global order consistent only for stores. So then total store order memory model and unique store order model. So there are actually proposals in that line. Or for example, how about enforcing a global order only at the boundaries of synchronization? Which we get to that with relaxed memory models, so whenever you have, for example, some critical sections, and then you have some synchronization primitives, you make sure that those related to that critical sections are actually ordered correctly, like all processors are observing the consistent view. But other load and stores which happening in the code, which they are not related to that shared address space, they can, work at any order. Okay, so we don't care essentially because they are not operating on the shared address space, and that's a key insight how people try to weaken this consistency model. They propose, for example, weak consistency model, release consistency model, and so on and so forth, which we're going to see them very, very quickly now. But we also discuss about these performance enhancement techniques that they could make sequential consistency implementation difficult, out of order execution, and also caching, which I don't want to repeat it again. Okay, so weaker memory consistency. The ordering of operations is important when the order affects operations on shared data, when processor need to synchronize or to execute a program region. Weak consistency, the idea is that programmer specifies regions in which memory operations do not need to be ordered. And then we have some memory fence instructions to delineate those regions. And all memory operations before a fence must complete before fence is executed. And the second criteria is that all memory operations after the fence must wait for the fence to complete. So you have these fence instructions. There are other names also in different ISA, but essentially you make sure that all memory operations before the fence, they should commit, they should complete before we want to execute the fence. And all memory operations after the fence, they should wait until we finish the fence instruction. So that's a weak consistency model, for example, that has been proposed. And fences, they complete in program order. So all synchronization dependent operations act like a fence, essentially, in that sense. So, yeah, so I don't want how much I want to explain. But you can actually read this because we are also not going into detail of that also about this weak consistency model. But there is this paper that they discuss 2 different techniques to enhance performance of memory consistency models, which in this paper they discuss about different consistency models. It's a beautiful paper in a sense that provides a rich literature review on different consistency model, and also the 2 techniques that they propose is also very interesting. But there are also other ways, which I think I can read something like here. So under sequential consistency, every access within the critical section is delayed until the previous access completes. But such delays are unnecessary if the programmer has already made sure that no other process can rely on the data structures to be consistent until the critical section is executed. So that's a weak consistency model, essentially, that you have this acquire lock and release lock, and you make sure that all operations before release A, for example, before acquire A, or memory operation, they need to be done, but at any order, but they should be done, they should be complete, and then you start executing this lock, and then you enter your critical section. And when you want to release your lock, you need to make sure that basically all memory operations after releasing lock, they should also wait for that to be done. Yes. Yeah, kind of. Yeah, exactly. Yeah. But there's also another way of actually you can go one step more between weak consistency. They get to this release consistency, which one step forward. Let me show you here. That essentially these techniques actually talks about releasing is not very important. Acquiring is much more important. So essentially, when we acquire A, we can potentially start executing. So we can execute this basic block 2 for sure. But then we can also start execute. We can schedule a load stores for this block 4 as well, because releasing is not very important. So you need to read the paper for more detail, but essentially that provides us more opportunity to parallelize the application. However, for example, in order to run this block 6, you need to pass this pass. Essentially, you need to acquire A, and then you need to acquire B, such that you can get this basic block 6 done. So that gives also kind of a way such that we can request for lock B also, in advance. So maybe you know that. So when you get the lock A, you can also start requesting for lock B, such that you can start executing this load store essentially in the basic block 6. So that gives you more opportunity to parallelize your application and potentially improve the performance. So there are many actually ways to weaken the consistency, and there are a lot of papers in that line. But I think you get the high-level idea of that. I hope so. Okay, so more, you can check this paper also. But there is a trade-off that essentially the good thing is that no need to guarantee a very strict order of memory operations, which enables the hardware implementation of performance enhancement techniques to be simpler and can be higher performance than stricter ordering. But as disadvantages, now we have more burden on the programmer or software. So as you weaken the consistency model, then you're actually relying more on the programmer. So the programmer needs to do more. Now the program, for example, needs to get the fences and the labeling of synchronization operations correctly. So that's one job. And also debugging would also become harder as you weaken the consistency model. But which is, here is also another example of the program microarchitecture trade-off. But in reality, also nowadays, because of the performance improvement of the system, and also to make sure that the hardware is not overwhelmed, we are actually supporting more weak consistency model. So that sequential consistency model in Lamport is actually too strong, and people are not really supporting that in today's architectures. Okay. You can also potentially have some other techniques which has been discussed in this paper that, for example, you can execute speculatively. So, for example, in this example, so I can speculatively think that I will get the lock. So I can enter the critical section, and execute that speculatively. It's kind of an optimistic execution model that you think that optimistically things are going to be okay, so I will continue executing. But then there should be a way to understand that what you have executed was correct or not, and you should be able to roll back and recover from wrong execution. So that technique also has been implemented a lot in the hardware, which is also very interesting. And you can actually check this paper. Is actually one of the very earliest paper in that line. There are also many other papers after that, but they also confirm the results and idea of this paper as well. So when you're doing speculatively, you do store actually, but the store is not happening in the actual memory. You might have some tables, for example, that you temporarily store in those tables, and you commit or flush the table when you make sure that what you have done was correct, essentially. So that's the kind of speculation execution. Because if you store in the memory, then rollbacking is actually very hard. You need to have a picture of the memory from the before execution such that you can roll back. Yeah, there are also other ways of supporting that with transactional memory, if you are also aware of that, which essentially some memory can be designed as a transactional memory, such that they make sure that these transactions that we have, we either run the whole transactions, all the transaction needs to be done, or we don't run any of that. So with transactional memory, you can also potentially support more this speculative execution as well. Any other question? So this topic, as you imagine, is going to be good for exam as well. So here I provide 2 example questions. You can check that. You can actually also find the solution online. But yeah, we might have some questions about that in there. Actually, it is not very hard. Like, for example, the first part is that list all possible values that can be stored in register R3 after both threads have finished executing. So in the end, talking about, okay, the consistency model that we have and two different codes, and depending on the order of the execution, you might get different values. So it's actually very fun to practice with these exercises. At least for me, I'm not sure. Okay, question. So I think let's take break for 15 minutes until 2:36. And then we will continue with cache coherence. Okay, here. Okay, let's continue. So now we're going to talk about cache coherence. I should also say that these topics that we are now focusing on the processor, kind of a processor-centric design, they're actually very important topics for memory-centric design as well. Like when you have several PIM engines, if you think about it, and then you want to parallelize your application across multiple PIMs, then you're going to get to the same problem. And how you make these PIM engines coherent and consistent, synchronized. So all these actually topics are also applicable in that sense, I'm saying that because that's actually open research problem that people are working on that. So if you're interested, you can actually also use this opportunity now that you know memory-centric computing, and also you're getting exposed to some traditional topics in computer architecture. You can think of, okay, how these topics are going to be in memory-centric computing. Okay, so cache coherence is happening because of the caching. So basically, caching not only complicates ordering of all operations, so which a memory location can be present in multiple caches, it also prevents the effect of a store or load to be seen by other processors. Makes it difficult for all processors to see the same global order of all memory operations. But it also complicates ordering of operations on a single memory location. So caching actually has effect on kind of consistency model, which makes it more complicated to support. But at the same time, it also complicates the order of operations on a single memory location. So we discussed about what's the difference between consistency model and coherency. And these are some papers. I thought I closed the door. These are some readings that you can check. Some of these papers we're going to discuss today, but some of them, they are just some optional readings for you to check. Okay, so many parallel action programs are using shared memory paradigm, as we also discussed, that these parallel programs communicate through shared memory, meaning that whenever they want to communicate, one processor would write or restore a value to a memory, and another processor we're going to read or load from that memory location. So it's going to be kind of a communication channel if you think about it. Instead of sending a message to another processor, you just use a location to put your message on that, and another processor would just pick up from that location. So that's why a shared memory model is, in the end, is going to be a communication way of implementing for synchronization and also implementing parallel applications. So essentially, if processor 0, for example, writes to mem address A1, then at some point, processor 1 wants to get this value and maybe print it, for example, assuming that this needs to be synchronized. So processor 1 should read which value, essentially. So each read should receive the value last written by anyone. And this requires synchronization. That what does last written mean here? So what if mem A is cached at either end, and then we don't know about the which one is the final result? So in this picture also you can see the problem that, for example, we have two processors that they wrote from the same memory address, and the value which for that memory address X is actually 1000. Okay. And at some point, one of these processors, they update that memory location with another value, which is 2000. And after some time, P2 is loading from that memory location again. So P2 should not essentially load 1000, assuming that this is actually a shared location. So that's a cache coherence problem that we want to focus on. So now the question is that whose responsibility is to provide essentially cache coherence. We're going to quickly discuss some software solutions, but we're going to dismiss them also because in the end, it's not very hard. It's not very efficient to support at the software layer for cache coherence problem. So now the first question is that can programmer ensure coherence if cache is invisible to software? So if cache is fully invisible to software, then it's very hard to provide any coherence support at the software layer. So there should be some visibility actually in the ISA provides to the software such that we can try to support that coherence at the software layer. There are some ways, for example, using that with coarse grain. For example, you can have page level coherence in your system. So whenever you're trying to make sure that not all like different, you're keeping the whole page coherent. So all updates should need to be coherent across all these processors. So now the problem is that you're getting to the false serialization bottleneck here. That there might be different locations in that page, which they are not really related to each other. But since you are operating this coherence at the page level, then you are potentially paying the overhead for all these updates and accesses. So which is not desirable if you want to do it at a very coarse grain. Another, let's say, non-solution is to make the shared logs and data non-cacheable, saying that, okay, we're not going to cache any of them. So then the problem is fixed from get-go. Or, for example, you can think of, okay, we're going to have a cache which is fully shared across all processors. So in this example, actually these caches are private. So that's why actually P2 is not seeing updates in the cache of P1. So these are private caches. If you make the whole cache architecture actually shared, then okay, everyone potentially are aware of all the updates and changes. But then the problem is the scalability. You know, how we can make this shared cache across all when the number of processors are getting increased. So some people actually work on combination of non-cacheable and coarse grain. So there are some works in that line, but there are also some works in the line of supporting software coherence, cache coherence protocol, very fine grain. So you really want to make sure that you're keeping the coherence at the block level. Then actually the ISA needs to provide some instructions that you can communicate with the cache. Like for example, you need to have an instruction flush local A, which this flushes or invalidates the cache block containing address A from a processor's local cache. So there should be these instructions in the ISA, and then the programmer or compiler needs to use this instruction to make sure that all local caches are coherent. Or for example, flush global, that you flush basically, or in flush global A, you flushes the cache block containing address A from all other processor caches. For example, you want to have this cache block exclusively, then you want to make sure that other cores, they don't have it. So you send this flush global A to make sure that everyone invalidates, and that core actually has the exclusive copy of that cache block. Or for example, flush cache X, that you flush invalidates all blocks in that specific cache. So there needs to be different instructions that programmer needs to work with them in order to make that the cache coherence work. So you can see that in the end, it's going to complicate the job for the programmer, and that's why actually in many of today's architectures, people are supporting cache coherence at the hardware level. There are actually some works in the past that people try to do it mostly at the software, but those projects also were not that successful in the end as well. So because if you don't make the job for the programmer easy, or at least somewhat easy, then no one is going to use the architecture, for execution. So that's a fundamental issue that is happening here. But in hardware, actually, it greatly simplifies software job. And one simple idea would be invalidate all other copies of block A when a core writes to A. So we're going to see an example here, how we can, for example, simply provide this coherence. We just call it valid invalid. We can make up this valid invalid protocol. But then we're going to see more sophisticated protocols through in this lecture. So assume that your local caches are actually write through, and they also no write allocate cache. So write through, I think you know, meaning that when you update a cache block, you immediately also update the memory or the lower levels of the caches. But no write allocate means that when you have write miss in that local cache, you don't bring the cache block to that local cache to update it. So you update only the memory. So that's why it's no write allocate. So now you can have you can think of this protocol. So for each block in cache, we are either in the valid state or invalid state. Okay. So assuming we are in the invalid state, meaning that we don't have this cache block essentially. So every read is going to be miss or write is going to be miss, right? So you're in an invalid state, and then the processor. So when you are thinking about this coherence protocol, you need to think about the view of the processor and also the view of the bus, because there is also bus which you're observing the changes or requests on other local caches. Okay, so there is a bus shared across these local caches, and you're observing through that bus the operations happening to other local caches, for example. So that's why we have different, essentially, signals here. PRWR is going to says processor write, and this one is processor read. This one is bus write, meaning that other cores are writing to this cache block. So the processor that here we are talking about is not writing, but other processor is writing, and we observe on the bus that someone is writing. So that's a signal of bus write. Or for example, bus read, meaning that some other cores are reading this cache block, and we are observing through the bus. Make sense? Okay, now that we understand these signals, we are in the invalid state, and we observe, we do processor write. So it's going to be a miss, okay, because we are in the invalid, and since we are we have no write allocate, so we stay in the invalid state. Okay. If we also observe bus write, meaning that some other cores are writing to this cache block, we essentially stay also in the invalid state, because we didn't have this block, so we don't care also that other cores have it. Okay, we stay in this invalid state. If we are in invalid state but we do read operation, we go to the valid operation. We go to the valid state because we are reading and we are bringing this cache block to the cache. If you also observe yeah, this part is a bit bus read, we go to the valid. Okay, yeah, in this protocol, we are saying that, okay, when we are also observing bus read, we can also potentially go to the valid state such that we have this cache block in our essentially in our caches. When we are in the valid state and we receive, we do processor read, we actually stay in the valid state. But when we do processor write, also we stay in the valid. Oh, sorry, this bus write is actually from this core to other. So when we do processor write, we stay in the valid, and also we send this bus write to other cores. And yeah, and we are, yeah, this is a kind of an output. In this slash means that the output. We do processor write, and also we signal bus write for others. But if we are in the valid state and we receive the bus write command, then we actually go to the invalid state, because other cores are writing to the cache, and we should invalidate our copy. So that's the main thing here. I think I got confused a bit here because this slash is not this and that. Actually, you do processor write and also you signal bus write. Okay, that's the meaning of this here. It's kind of a output for that milli state diagram that we have here. Okay, so this simple protocol works, but any question? It's not very efficient protocol, of course. For example, the fact that we are not allowing write back caches, in this cache, or for example, we have no write allocate. So these are all inefficiencies of this protocol. But this is simple and works. But any questions about this protocol? Okay. So as we discussed, there are some solutions that I would like to call them non-solutions to cache coherence that come up with a no hardware-based coherence. So that's actually keeping caches coherent is a completely software's responsibility, and that makes microarchitecture's life easier, but makes average programmers' life much harder. They need to worry about hardware caches to maintain program correctness, and overhead in ensuring coherence in software, page protection, page-based software coherence, non-cacheable, and other techniques. So that's, in the end, people try to go with completely at the hardware or something between, hardware software solution. But completely at the software without any changes to the hardware is not a good solution. Or another non-solution is that we consider that all caches are shared between all processors. So no need for coherence, of course, but then shared cache becomes the bottleneck, and very hard to design a scalable system with low latency cache access, this way. So like L1 cache, the processor needs to access it fast. Now that assume that the L1 is can be shared across all processors, then when you are accessing L1, you might need to actually go several hops, through the network in order to get your data from the L1 cache, which can actually increase the latency of L1 accesses, and then in the end is going to come with the performance overhead. It also complicates the pipeline design of the processor because of the variable latency that you're observing at the L1 cache access, for example. It might be very local to you, or it might be very global, far from you. So you're going to see different latencies for that L1 cache access. Okay. So how to maintain coherence? We need to guarantee that all processors see a consistent value or consistent updates for the same memory locations. So writes to location A by processor 0 should be seen by processor 1 eventually, and all writes to A should appear in some order. So now the coherence actually needs to provide is actually two primitives: write propagation, which guarantee that updates will propagate, and write serialization, provide a consistent order seen by all processor for the same memory location. Make sense? Okay. And that's why we need a global point of serialization for this write ordering. So in that simple protocol, we use the bus interconnection. So all caches are connected to the bus, and they are using the bus for the point of serialization. But there are other ways of doing that, which we're going to see also very soon. So this hardware cache coherence, the basic idea is that a processor or cache, in this lecture, actually, we are using processor and cache interchangeably. They broadcast, write, and update to a memory location to all other processors. And another cache that has the location either updates or invalidates its local copy. Sometimes some cores, when they actually update, they broadcast also the data, not only saying that invalidate. They also broadcast the data, and other caches that they have this copy, they can actually update, okay? But that also comes with a trade-off in the end, which we're gonna also discuss later. So now the question is update versus invalidating. How can we safely update replicated data? So one option would be having update protocol that we push and update to all copies. So when a core updates a local cache copy, we also push the update to all other copies that we have. So with that, you need to send also the data. It's not only sending the invalidation signal. Another option would be invalidate protocol that we ensure that there is only one copy local and we update it. So the other cores, they need to invalidate their copy such that when they in future, when they want to access that cache block, it's going to be a miss, and they go through the memory and then get the hopefully updated value. So they should not read the stale value in the end. So on a read, if local copy is invalid, we put out request. If another node has a copy, it returns it. Otherwise, memory does. So that's the update protocol essentially. On a write, read block into cache as before. However, in update protocol, we write to block and simultaneously also broadcast written data and address to sharers. But in and other nodes update the data in their caches if block is present. In invalidate protocol, write to block and simultaneously broadcast invalidation requests to other sharers such that they invalidate their copy. Make sense? Okay. So which one is better, update or invalidate? In the end, depends on your access pattern, essentially. So on write frequency and also sharing behavior are critical. So in update, if share set is a constant and updates are infrequent, this can actually avoid the cost of invalidate and reoccur and also this broadcast update pattern. So in such cases, actually, it's good to update. And also downside of update is that if data is rewritten without intervening reads by other cores, that update would be useless. So so essentially you send the update to other cores, with the hope that when that core very soon needs to read that cache block, and then you want to make sure that that core is going to read the updated value. Okay, that's why you send a copy. But if that core is not going to read from that cache block anymore, so that update is just useless. Okay. And usually with this update protocol, we need to use write-through cache policy, which in the end, bus can become a bottleneck also, because you need to put out the data on the bus, and you are spending more on the bandwidths of the network that you have. However, in invalidate, after invalidation, core has exclusive access rights. That's very good, meaning that when you have exclusive access, you can actually update your exclusive copy silently. We're going to see how we can use that. But that will simplifies essentially some of the, or reduce some of the coherence traffic that you might have when you know that you have exclusive access to that cache block. And only cores that keep reading after each write, they retain the copy. So on average, you're going to see that behavior in the end. However, if write contention is high, that leads to ping-ponging, essentially. So rapid invalidation and reoccurring traffic from different processors, meaning that different processors are updating, on same memory location. So with this invalidate copy protocol, they're gonna essentially you're gonna get to this ping-ponging, essentially. That they invalidate. So you update, you ask them to invalidate, and very soon they also need to update. So then you ask you to invalidate. There's going to be a lot of ping-ponging between different cores, which comes at the overhead. So in the end, it's very much, it depends on the write frequency and also sharing behavior of the application. This can be also kind of dynamic as well. So depending on at runtime, you might be able to actually choose, if you consider that reconfigurability in your protocol, you can potentially combine these techniques as well. So there are two famous cache coherence methods. One of them is Snoopy bus, which the protocol is actually bus-based. So we are relying on bus as a single point of serialization for all memory requests, and processors observe other processor actions through that bus. So we are snooping on the bus to make sure that everyone is coherent. Like when processor 1 makes a read exclusive request for A on bus, P0 sees this and invalidates its own copy of A. So everyone is observing on the bus. Another way is directory, which single point of serialization per block. It can be also distributed among nodes. It can be also centralized, but mostly is actually distributed to make sure that it's we don't get to this essentially bottleneck that you have only one node that everyone is going to accessing that. But essentially with directory, processors make explicit requests for blocks, and directory tracks which caches have each block, and directory coordinates invalidations and updates. So in a Snoopy bus, we don't know essentially what cores they have or they may not have the. I mean, we can if we have this exclusive access, we know that other cores they don't have it. But in general, for example, when you want to send an invalidation request, you don't send that invalidation request to a specific core. You just put the invalidation request on the bus. And other cores, they would act on invalidation requests if they have that cache block. So that's a Snoopy bus protocol. But in directory, we are essentially we're explicit. So directory knows that this cache block is actually shared or not. And if it's shared, actually, which cores they have the copy. Then directory will send the invalidate request only to those cores that they have the copy. So that can potentially reduce the, some coherence overhead, coherence traffic, but also it comes at other overheads, which we're going to also discuss it later. So quickly, I will go over directory-based cache coherence, but through the end of this lecture, we're going to get back also to directory again to revisit and see more details. But you got the idea of a directory-based coherence, that a logically central directory, it can be actually implemented physically distributed, but logically is actually central. So there is logically central directory, keeps track of where the copies of each cache block reside. And caches consult this directory to ensure coherence. Like an example mechanism is that for each cache block in memory, you can store p+1 bits in directory. And one additional bit is actually for indicating that whether the block is in cache. This one additional is to show that we have this exclusive or not. And the other bits is one bit for each cache. So when we have P processors, we have P local caches. So that's why we are storing P bits. And this extra bit is for exclusive bit, essentially. So on a read, we set the caches bit and arrange the supply of data. And on the write, also, we invalidate all caches that have the block and reset the bits. And then we can also set this exclusive bit when we write to that cache block, showing that this cache has the exclusive copy of that block. So here is an example of directory. For example, for block A, the initial actually bit vector is all zeros, meaning that, assuming that we have 4 processors, for example, here. So meaning that this block does not exist on any of these local caches. At some point, P1 takes a read miss to basically onto block A. So then directory is going to be updated to this value, which we set the corresponding location for P1. And then P3 takes a read miss after some time. Then actually directory is going to update the sharer set. So directory keeps track of cores that they have these blocked, essentially. At some point, P2 actually takes a write miss. Then directory is going to send the invalidation request to P1 and P3 only, and then send the write request to P2, and then we also set the exclusive bit here. Okay, that because P2 is writing to that, and then it's going to be exclusive access. There should be also in the local cache of P2 or all processor, there should be also additional bit for that exclusive access, exclusive copy as well, just to make sure that we know. Because so the idea is that, when the core has exclusive access to a cache block, the core does not need to go over the directory. Because every time we want to consult with the directory, it is an additional step, the latency overhead that you need to consult with the directory and then act on based on the consultation. But if you have exclusive copy, then you don't need to discuss with directory at all, okay? So that's why at the local caches, we also need to have some bits to show that for this block, actually, we have exclusive copy. You can potentially store it in the tag array, for example, of that block. Okay, so after some time, P3 takes a write miss. Then we essentially update the shared set. And now still is exclusive, but here is exclusive to P3. And when P2 takes a read miss, then actually we update the shared set. Now we have these two, all of them one. These two are ones. And then it's not exclusive anymore. So we also reset the exclusive bit also to 0. Make sense? Okay. So there are a lot of optimizations that you can think of for directory. So directory is the coordinator for all actions to be performed on a given block by any processor, which guarantees correctness and ordering. But there are a lot of opportunities for optimization. For example, it can be enabled by bypassing the directory and directly communicating between caches. Like that exclusive bit that we also discussed is kind of optimization. We already consider that we have that optimization. But when you have exclusive copy, you don't discuss, you just bypass the directory. But there might be also ways that in such cases, you might, assuming that that's controlled way, somehow we need to make sure that we are still coherent. But people are trying also sometimes to bypass directory and directly communicating between caches. We'll see some example optimizations later, but when we revisit this directory. Question? Yes.
For example, if you have this tool, then you can try to schedule the parallelism in a way that most of the on a second.
Yeah.
So that there is less contention.
Yes. Yeah.
And those ideas
Yes.
So that those things are
Yeah, yeah.
And then you can basically minimize the invalidation.
Yeah, yeah. Yeah, I agree. Actually, that was the topic of the lecture that we are not covering this semester. But essentially, yes, when you have critical sections, you can schedule them on large cores. And to make sure that most of the variables for that critical section are also kept in the private cache of that large core, there's going to be more heat also. So that paper, data marshalling, is also related to that, how you map your data. But one part of your comments, I want to correct here that the critical sections, but those critical sections are part of the parallel portion. So you already spawn threads, and all threads are actually running the code. And critical section is also part of that code. So you cannot, you can try, but it's not very also efficient to say that it might not be easy also. From the get-go, say that, okay, this critical section needs to be executed on the large core. Because these codes are, that critical section is part of the code which that thread is actually running. That's why we are discussing about scheduling that. So by using techniques like remote function call, for example, you say that, okay, this part, when I get to this critical section, I just do remote function call. That try to run it on the large core, essentially. Yes. Yeah, exactly. And that's actually the idea of bottleneck, like bottleneck identification. The paper, we try to count like how many threads are stalling or waiting because of that critical section. So that gives us some idea that this is a bottleneck, and then we try to schedule that. And yeah, those papers actually, they are in that line. I recommend you check those papers, and then yeah. But you're thinking very good, actually. Yeah, that's correct. Okay, any other question? So now let's get to Snoopy cache coherence also a bit more. Hopefully after that, we will have another short break, and then we will conclude. Okay, so in a Snoopy cache coherence, all caches snoop all other caches, read-write requests, and keep the cache block coherent. Each cache block has a coherence metadata associated with it in the tag store of each cache, essentially. Easy to implement if all caches share a common bus. That's why actually Snoopy cache coherence has been implemented for multi-cores when we have, for example, 8 cores, 16 cores or so. But for example, when in a many core system, when you have 1,000 cores, for example, Snoopy cache coherence is not that feasible, because having a bus interconnection connecting 1,000 cores is not scalable in the end. There are actually ways people try to come up with virtual bus in the interconnect. So we're going to have lectures on interconnect actually next week, hopefully. But in the interconnect, you have different topologies, and then potentially you can also come up with some virtual bus in that interconnect, and then use that virtual bus for your Snoopy cache coherence, for example. But those also are very costly and not easy really to implement. Okay, but when you have this bus, things are easy with the protocol at least. So each cache broadcasts its read and write operations on the bus to inform other local caches. And as I say, it's very good for a smaller scale multiprocessor. Okay, so in this example, for example, we have n processors, and we have n local caches. And this is the tag array, which now we also keep the metadata for the coherence. And it's a shared bus and the memory, essentially. So in a Snoopy cache, we can actually have actions from the processors to a block, like processor read and processor write, and then bus actions to a block, which is happening from other processors, like bus read, bus write, or bus read X, which is bus read exclusive. Sometimes you're getting this request that someone is reading this cache block exclusively, which we will see how we can use it. So this protocol that we have seen actually in the beginning of this lecture was actually using a Snoopy cache protocol, which was a very simple protocol, and we call it VI protocol. We just made it up, valid invalid. But now we want to extend this protocol and make it more complicated, optimize it to be better. So what if we want write back caches? So we want to have a modified state, because in this protocol, we don't allow write back. We say that we have cache is write true. So now a more sophisticated protocol is MSI, modified, shared, and invalid. So we have 3 states in this protocol. Modify is cache line is the only, cache line is the only cached copy and is dirty. Shared cache line is one of potentially several cached copies, and it is clean. But it doesn't say that it says that it is potentially shared, because we don't have this exclusive copy, state. So when we are in the state of shared, the thing what it says is that this cache copy is actually clean and is also potentially shared across other cores. But it might not be also true. It might be only that one core that has that essentially copy. Okay, so that's a limitation of the protocol, because we don't have a state to differentiate between exclusive or shared states. And also we have another state which is invalid. Cache line is not present in the cache. Okay. So when we have read miss, that makes a read request on the bus, and we transition to shared. And write miss makes a read exclusive request, and we transition to modified state. When a processor snoops read exclusive from another writer, it must invalidate its own copy, if any. And shared to modified is called an upgrade, because it can be made without accessing memory via invalidations, essentially, because we are allowing modified state in this protocol. So this is the state diagram of it. I don't want to go into all of these transitions, but maybe some of them. So when you are in the shared state, it means that you have the block, and this block is clean. So if you get this processor right, you send this bus read exclusive on the bus, and then you move from the shared to the modified state. And when you're in the modified state, you can, whenever you get processor read, or whenever you do processor read or processor write, you stay in the modified state, because you have the exclusive access. But at some point, if you're in the modified state and you get bus read, you get back to the shared state and you flush. Essentially, you say that, okay, now another core wants to read, so I cannot stay in the modified state. I need to go to the shared state, but I will also flush, because I have the copy of this block. So I flush such that other cache also get the updated value of that block. But this flush can actually happen. It can be through the memory, such that that modified cache we flush to the memory, and then another cache gets the updated value from the memory, or it can be also directed pass from this cache to another cache, such that we just copy the data. But essentially, that's the implementation detail, how you really implement and support this protocol. But essentially, when you go from modified state to shared state, you need to flush your data. And when you get this bus read exclusive access, like another core wants to read this block in an exclusive manner. So you go to you still need to flush, but then you go to the invalid state, because you're not allowed to have this block anymore, because the other core needs to have it in a exclusive access. Make sense? Okay. I think we discussed all of them. Yeah, here also, when you're in the shared state and you get bus read exclusive, you go to the invalid state, because we are not allowed to have it. Okay, but MSI also has its own problem. So a block is in no cache to begin with. So now the problem is that on a read, the block immediately goes to the shared cache, shared state, sorry. Although it may be the only copy to be cached, no other processor will cache it. So why is this a problem? I mean, you can guess why is it a problem, but so just to elaborate, suppose the cache that reads the block wants to write to it at some point. Now it needs to broadcast invalidate, even though it has the only cache copy. So we read, on a read miss, we go to the shared state, assuming that also, like in this example, we are thinking of that cache block does not exist on any core, any other cores. So we go to the shared state, because we don't have any other state to reason about this situation. And then when from the shared state, when you want to go to the modified state, you need to send this bus read exclusive. So you need to send that essentially invalidation request. You need to broadcast it, say that, okay, I want to modify it. Whereas if you know that you have the only copy of that data, you don't need to broadcast that information. You can just go to the modified state and update. And that's the reason we want to have this exclusive access. So if the cache knew it had the only cache copy in the system, it could have written to the block without notifying any other cache, which saves unnecessary broadcasts of invalidations. Make sense? Yeah, essentially these are the problems. So now the solution is protocol MESI, which we add another state indicating that this is the only cache copy and it is clean, which is exclusive state. Block is placed into the exclusive state if during bus read, no other cache had it. So there should be a check at the implementation. Whenever we want to read and bring that block to the cache, if other caches, no other caches have that block, then we can actually go to the state of exclusive. So this can be implemented easily with wired OR, shared signal on bus. So essentially, it's easy. So other old cores can assert the signal. If the OR of them is 0, meaning that basically, so you put this bus read request on the bus, and all cache blocks, if they have this block, they will just assert a signal. If they don't, that signal is going to be 0. And then if you wired OR those signals, it's going to be 0. And then if you check the value of that wired OR, you're going to see 0, and meaning that no other caches have that copy, and you can go to the exclusive state, essentially. So now the silent transition from exclusive to modified is possible on write, which makes a lot of difference. MESI is also called the Illinois protocol because it actually has been proposed in this paper by, I think it was a master students of Patel, no? I heard, or maybe bachelor students. But yeah, MESI protocol is very famous. You're gonna also learn more about MESI state machine in because you're gonna do that. I mean, optionally, as lab 7, I guess, optional bonus lab if you're interested. But yeah, so essentially in MESI state machine, when we are in invalid state, we can go to the exclusive clean if on bus read, on processor read, and only that processor has that copy. So we go to this exclusive clean state. And when we are here, we can actually go silently, we can go to processor write. We can go to the exclusive modified state. There are different actually versions of this MESI, which I'm showing here, different state diagram that you can also check them at home if you're interested. But yeah, this is going to be actually bonus lab 7, not 6. I think we have, yeah, bonus lab 6 is going to be related to virtual memory, which tomorrow you're going to learn about virtual memory. So the thing is that these protocols make sense, but when you want to implement them, you're going to get to a lot of issues. So implementing them is not that also easy in the end. You're going to get to a lot of race conditions, for example. So to make these protocols work, actually, there needs to be a lot of work and testing, and that's why actually these cache coherence protocol, we're going to also improve this protocol a bit more. But at some point, it's not worth it because you add more state and states, but then that complicates the design more and more, and that complicates the testing also. And at some point also it's kind of you don't get also a lot of improvement as you add more states to this essentially protocol. But yeah, it's going to be your bonus lab 7. I will update this slide, which you're going to see that this has been also implemented in Intel Pentium Pro coherence protocol. A master thesis project. Amazing. Okay. So now let's get to this trade-off also, because we want to add another state potentially to this MESI protocol. So now the question is that a downgrade from modified, we should go to the shared or invalid state. So if we downgrade from modified to shared, if data is likely to be reused before it is rewritten to by another processor, we go to the shared state. And downgrade from modified to invalid if data is likely to be not reused before it is rewritten by another. Then we need to have these cache-to-cache transfers. On a bus read, should data come from another cache or memory? So another cache may be faster if memory is slow or highly contented, but memory is simpler. No need to wait to see if another cache has the data first, less contention at other caches, and requires write back on modified downgrade. So write back on modified to shared needed since shared state is clean. So that's the assumption in the messy protocol, that also in MSI, that shared state is clean. So when you go from modified to shared, you need to essentially write back your data. So can we avoid this write back to memory? That's one possibility, that people come up with this Moisey protocol, one version of it, that they have this owner state. That so we try to designate one cache, so that the one cache owns the latest data, and memory is not updated. So at some point, if we're gonna remove that cache block or evict that cache block from the caches, that owner is responsible to update the memory. So you designate owner just to make sure that eventually you're gonna update the memory. So so I'm gonna discuss a few optimizations on messy. So one observation is that shared state requires the data to be clean, meaning that all caches that have the block have the up-to-date copy, and so does the memory. So this problem is need to write the block to memory when bus read happens, and also when the block is in modified state. So why is this problem? Memory can be updated unnecessarily. Some other processor may want to write to the block again. And then we can improve messy to avoid that, essentially. So one idea is that do not transition from modified to shared on a bus read. We invalidate the copy and supply the modified block to the requesting processor directly without updating memory. Another idea would be transition from modified to shared, but designate one cache as the owner who will write the block back when it is evicted. So now in this case, shared means shared and potentially dirty in this protocol. This is a version of a Moisey protocol. So of course, there's a trade-off here. The protocol can be optimized with more states and prediction mechanisms that reduce unnecessarily invalidates and transfers of blocks. But as we add more states, they are more difficult to design and verify. And at some point also it provides diminishing returns, meaning that from that valid-invalid protocol, when we go to MSI, we get very good performance improvement. From MSI to messy also, we are getting somewhat good performance improvement, but from messy to Moisey, we don't get much. And then from Moisey to more and more, we don't get also that much performance improvement such that justify the complexity that we are adding to the protocol. Okay. So before quickly revisiting the directory, maybe we can take a short break until 3:35, and then I will continue and hopefully conclude today's lecture. Okay. Yeah, thanks for bearing with me. Now let's also quickly get to more optimization in directory. So Snoopy Boss, I think you got it. Like the idea is simple. The main issue with the Snoopy Boss is that we are relying on boss, and having a boss as a serialization point is not scalable. So as you increase the number of processors, having that boss is not easy. So that's why also people look into directory as well, which is more scalable in that sense, because you can also design this directory distributed in your system, and then you can potentially have better scalability. So just to quickly compare Snoopy cache. So in Snoopy cache, actually miss latency or critical path is short because you do send requests and then you have bus transaction to memory. And the global serialization is easy, assuming that we can have that bus. So because that provides this already with the arbitration that we have. It's also simple, but relies on broadcast messages to be seen by all caches in same order. So that's why we are using bus here. And that's essentially one of the main problem with the Snoopy cache. Yeah, so we can have virtual bus or totally ordered interconnects, but that's also not very easy. How we can implement virtual bus through the routing algorithm, through the flow control of the network on chip is not very easy. There are works on that line, but yeah, not really easy to implement. But with directory, so the main issue, one of the issues is that it adds indirection to miss latency and critical path. So whenever you have a request, you need to consult with the directory. So there is another step in between, which gonna increase your critical path essentially. And it requires extra storage space to track share sets. But that can be approximate because false positives are okay for correctness at least. So you can think of using techniques like Bloom filter, for example, here, for this directory as well. That bit vector can be stored in a Bloom filter essentially, which makes sure that you don't have false negative, but false positives you might have. But false positives are also not good for the performance reason. You might send some invalidation request unnecessarily. With directory, there might be also protocols and race conditions that are much more complex for high performance. But the good things about directory is that it does not require broadcast to all caches, and exactly as scalable as interconnect and directory storage. So as much as you can scale your interconnect, you can also scale the coherence protocol that you have. So just to recall, a directory, we have a logically central directory to keep track of where the copies of each cache block reside, and then caches consult this directory to ensure coherence. This kind of a example mechanism that we discuss it, and we've seen also this implementation. So directory-based protocol, it required when scaling past the capacity of a single bus, it is distributed. So coherence still requires a single point of serialization for a given block for right serialization. But that directory is logically central, but when you are implemented physically, it can be actually distributed. So serialization location can be different for different blocks. And so you can actually partition the blocks that each directory partition is handling. And so depending on which block you're accessing or you're concerning, then you are accessing different directory partitions essentially. So now we can reason about the protocol for a single block, one server, like directory node can be considered as a server, and there are many clients that essentially private caches. So with directory, you have this client server actually paradigm, which that gives us also some optimizations on the protocol. And also directory receives a read and read exclusive request and sends an invalidation request. So invalidation is explicit here, as opposed to a Snoopy bus that you just put an invalidation request on the bus, but here you send the invalidation request to those caches that they have the copy, because you are keeping the sharer set of that cache block. So here is an example data structure that for each block you are setting as keeping the shared set, and also you're keeping that some like for this block P2 has the exclusive access. So this is required to support invalidation and cache block requests. So the key operation here is to support a set inclusion test, which, as you can imagine, false positives are okay in terms of correctness, but not in terms of performance. So we can actually try to, reduce the space by using techniques like Bloom filter or so. There are also works that people compress essentially the directory using compression techniques. But if you want to have accurate and expensive, then you need to have this full bit vector, which is going to be very expensive. But as I said, compressed representation, linked list, Bloom filters, they are all possible. And there are different works that they use that. So there are some basic operations here for essentially for directory, but they are also actually following semantics of a Snoop-based system, but with explicit request reply messages. So with directory, directory receives a read and read exclusive, and then upgrade requests from nodes. And directory sends invalidation and downgrade messages to sharers if needed. And directory also forwards requests to memory if needed. And directory replies to requester and updates sharing state. So now with directory, actually, protocol design is flexible, and exact forwarding paths depends on implementation. So essentially, now that you have this directory, you can potentially also change your protocol, as you want to, basically, after some time, if you want to improve the performance. Whereas in a Snoopy cache, it's very hard to actually update the protocol because you are considering some those metadata for the Coherence protocol, and you are adding those metadata in your tag array, essentially. And so at some point, if you want, for example, to go from MSI protocol to MESI protocol, it's not easy to do it without changing the hardware. But with directory base, you can potentially also change the the policy in the directory. You can think of, okay, some reconfigurability I can consider in directory. There might be some parameters. It can also potentially have different codes that you need to run for directory, which essentially gives you flexibility to to test and change different Coherence protocols. So I'm going to show you several examples here with directory. You can also think of messy directory transaction. So we have still a messy protocol here, but we are not implementing it using a Snoopy cache. We are implementing using directory. So on read, P0 acquires an address for reading. So we send the read request to the home directory, and the directory actually send the data exclusively to the P0, for example, or for example, send this to the in a shared manner. There might be some other, so in a shared manner, when there is other cores also, so directory can send to P1 and then P1 send to P0. Like it might be also the case that P1 has the updated value, so directory asks P1 that P1 sends the data to P0. And read exclusive with former owner also. With P0, we send a read exclusive request to the home directory, and then home directory send the invalidation request to the owner. Owner send the updated value because this owner is responsible to supply the updated cache block. So the owner sends this value to the home directory and also send it to the P0 as well. Also with directory, you can handle contention. You can resolve contention like P0 and P1 both. They are reading requesting for the same cache block exclusively. And at some point, the directory actually reply to P0, for example, and then send the negative acknowledgement to the P1. So that makes P0 happy and P1 sad, but at some point, after some time, so essentially P1 needs to retry. P1 retry, and at some point, the home directory will send the invalidation request to P0, and P0 will send the data to the P1, and then the P1 also will be happy at some point. Okay? But there are issues with contention resolution here that we need to escape race conditions by negative acknowledging requests to busy or pending invalidates entries. So original requested, those requested, they need to retry. Or we can queue requests and granting in sequence. So that's also another implementation. Or it can be also combination of both. Here also we have this fairness issue, like which requester should be preferred in a conflict. Interconnect delivery order and distance also both matter. Like there might be, so the directory is distributed in the chip, in the SoC, and then there might be some cores that they are closer to the directory, which is responsible for those cache blocks. So now if two cores that they are accessing or requesting for the same cache block, one of these cores are close to the directory, another one is far. So that one is close, you will get access quickly to the directory and probably will get the service. But the other one, which is far from the directory, will always get essentially deprioritized because you get to the directory probably later. So then we're going to have this fairness issue here, which needs to be handled in some way. So that's why we are saying that interconnect delivery order and distance, they all matter here. And ping-ponging can be also reduced with protocol optimizations, so at the hardware, or also better high-level synchronization. So at the software, we can also try to write better codes, essentially, to reduce ping-ponging. Yeah, so there are solutions like combining trees with for logs and barriers, and also better shared data structure design, which I don't have time to go over them, but you can check if you're interested. Actually, these are, I think, taught in parallel programming courses. Have you guys taken those courses? Yeah, it's interesting to learn more about these topics. Now that you know the hardware, it's also interesting to know how we are implementing parallel programs, and then potentially come up with hardware software solutions. Okay, so some basic question like how large is the directory? How can we reduce the access latency to the directory? How can we scale the system to thousands of nodes? And can we get the best of snooping and directory protocols, with potentially with heterogeneity? So there is this paper, Token Coherence, which actually nicely combine snooping and directory, which I recommend you checking this paper. But how large is the directory? These are actually very good exam questions, which is not very hard actually to calculate, assuming that you are storing p+1 bits. So you know the number of processors, and you also know the total number of cache blocks that you have. So then you can potentially calculate the directory space, right? And then that gives you some scalability idea, like how can we scale the directory? But also you should consider that directory is not implemented in a centralized manner. So directory is going to be partitioned across different nodes in the network, such that we keep the space, the storage of directory actually small. Also, another thing is that the real directory might not be actually in the SoC. It might be actually in the main memory. So we are caching directory also. So those things are also possible. That because directory can be huge, and then your space at the core is not enough, so such that you are using that directory in the core as a hardware cache for the actual directory that you might have. Okay, so this topic is also very interesting for exam questions. So you can for this example actually, you can also calculate the size of directory, like blocks per node, and directory storage per node, like 200 megabyte in this potential example. Yeah. Question? Okay, very good. So, yeah, I'm going to conclude actually very soon. I just want to give you some intuition that these topics are actually very much active now, not in the line of multiprocessor, but actually in some other domains, which I actually mentioned in the very beginning as well. One interesting paper that I think we also briefly discussed it in our memory robustness lecture is that these people actually, they show that noisy cache coherence protocol actually can cause hammering, can cause RowHammer issues. So this paper is very interesting that they show that actually cache coherence, the traffic can actually exacerbate RowHammer, and then they come up with preventing that issue in this paper, which I recommend you check in this paper. It's a very interesting paper. Also, as I said, in memory-centric computing also, we also need to keep things coherent. I don't have time to go into detail of that, but essentially how we discuss about it in the adoption challenge of PIM, how to enable adoption of processing memory. There are potential barriers to adoption, like application and software for PIM, ease of programming, system and security. And you can see that coherence, synchronization, and essentially virtual memory isolation, they are all here in order to, to provide adoption of PIM. So these actually, all these five is research direction are very much active and very interesting actually to work on. So I recommend you, if you're interested, just just email us and we can meet and discuss. We have done some work in the supporting coherence for PIM. This one, the early version of this work, lazy PIM, and then later on in ISCA 2019, Conda, which is more sophisticated. But I'm going to explain this work very quickly. But I believe actually there needs to be much work in this line. So this paper, Conda, is also still very expensive and complicated to support. So there should be much more simpler solutions to this coherence support. But just to give you an idea, I don't have time to go detail in this paper, but essentially, I mean, you know about PIM. I mean, in this paper, the terminology is a bit different. We call it NDA, which is near data accelerators, but you can think of PNM, processing near memory. So the challenge here is that the coherence between NDAs and CPUs. So there's a large cost of off-chip communication, and NDA applications generate a large amount of off-chip data movement. So it's impractical to use traditional coherence protocols. So essentially what we are talking here is that the application that you are running, you partition some part of this application to the host CPU and part of it into NDA. And these applications, they are operating on the shared memory address space, which means that in the end, you need to keep this coherent. And so if you want to support that coherence using traditional techniques like messy protocol, for example, then there's going to be a lot of communication back and forth between the PIM and also the host system, which in the end is going to, you decided we are proposing processing memory in order to avoid data movement or mitigate data movement as much as possible. But now we are causing a lot of data movement to keep things coherent. So that's why this problem is actually very important. So let me get to some interesting part that I can explain a bit more. Yeah, these are about NDP. Yeah, in this work, actually, we look into some applications in hybrid databases and graph processing. So we find some observations here that not all portions of applications benefit from NDA. So which means that we do need to use both PIM and host CPU at the same time. So the first key observation is that CPU threads often concurrently access the same region of data that NDA or PIM kernels access, which leads to significant data sharing. So these two, PIM and host CPU, are actually operating on the same memory region or shared So that's why we need to keep it coherent. However, the second key observation here is that CPU threads and NDA kernels typically do not concurrently access the same cache lines. So even though they are operating on the same same memory address space, they are not concurrently operate on same cache lines. They may, but on average, for these applications that we tested, they don't typically do not concurrently access, which gives us actually the key insight of this technique in Conda, which I want to. We also had some analysis that we showed that essentially other solutions are not good. When you want to do this coherence, non-cacheable or coarse-grained coherence or fine-grained coherence, this fine-grained coherence is actually implemented using a messy protocol, for example. So there are actually results about that in the paper, like about all these prior approaches and how we can keep it coherent. And we show the results, essentially, that it's very interesting that, for example, with non-cacheable and coarse grain, you're actually getting lower speed up. You're actually getting a slowdown compared to the baseline CPU only. So you're using PIM, but because of the coherence protocol, you're actually sacrificing the performance. With fine grain, we are getting still better performance, but energy-wise, from the energy, we observe that fine grain protocol does not provide good energy efficiency. So, and this is the result for ideal near data accelerator, meaning that we magically think that there is no coherence need. So magically, coherence protocol has been solved, so such that you can just execute in PIM without any issue. So that will give you this gap, performance improvement, and also energy efficiency. Okay. Let me get to the key idea. Yeah. So basically, we leverage these two key observations that I mentioned. So the first key observation was that we have they are operating on the shared memory address space, and the second observation was that typically they are not touching the same cache block or cache line at concurrently. So because of the second observation, we can actually have this optimistic NDA execution. So whenever you want to whenever you are running these NDA kernels, you're just optimistically run it, assuming that no coherence violation is happening, because typically it's not happening. We know that from our results, right? Because NDA and CPU are not touching the same cache lines concurrently. So you can have this optimistic execution that CPU and NDA, they essentially runs together, I mean, parallel. So CPU starts optimistic execution of NDA, and NDA is doing it optimistically. And in this line, we have concurrent CPU plus NDA execution. So there is no coherence request, okay? But after some time, we need to do coherence resolution. So when this NDA is done, we check with some technique that essentially you can think of NDA keeps track of cache blocks that it accesses, and CPU also keeps track of cache block it accesses, and then NDA sends a signature of those cache blocks to the CPU, and CPU checks if there is a violation or not. If there is no violation, actually things are good, and NDA will essentially commit the result. But if there is the violation, then NDA needs to re-execute. So that's the overhead when we are doing this optimistically, okay? So we are not trying to resolve the coherence as we are executing. We just say that optimistically, there are not gonna be coherence violations, so I just execute. But at some point, I will check the signature, and if I see some coherence violation, then I will repeat the execution of NDA. But in order to make sure that we can do this re-execute and not commit until we are sure, then you need to add some buffers, tables, to make sure that you are not updating the memory location. You are just updating in a table, which that's also part of the problem which makes this technique costly. Yeah, so I don't want to spend more time on it. You can actually check these slides at home for more information if you're interested. But yeah, essentially, that's the technique of Conda. So if I just want to give you some quick results, because we are already late, a lot of things are changing here. Yeah. So for these applications that we tested, Conda actually provides, this is the performance improvement of Conda compared to fine-grained coherence protocol and also NDA only and CP only. And this actually also ideal NDA, which means that coherence has been resolved magically. So you can see that actually Conda is, bridging the gap between ideal NDA and fine-grained coherence protocol nicely here in terms of performance and also energy efficiency. Okay, I think I will stop here. But yeah, these slides are related to Conda. You can also check later. But as I said, there needs to be more work in this line to make it simpler and more effective. So if you're interested, just talk to us. Any question? Yes.
Is the problem solved for NDA unit coherence? Like one unit of NDA sees the exact same thing as the other. In terms of upmem, one degree sees the exact same thing.
So upmem, this problem does not exist because the memory address space of upmem is the disjoint of the host main memory address space. So they are not operating on a unified memory address space. This problem is actually causing when NDA and host CPU, they are operating on a unified memory address space, which eventually we want to get to that. But companies, industry, in order to have ease of adoption for now, they are considering this disjoint memory address space, similar to GPUs in the beginning, if you think of it, if you will. Yeah. Very good question. So tomorrow we're gonna discuss virtual memory. It's gonna be a very interesting lecture. And next week we're gonna have, I guess, 2 lectures on interconnects. And the week after is gonna be the exam on Thursday. And on Friday, we're gonna have some cutting edge research presentation. So if you're, still around, you can actually attend that lecture and also learn about some cutting edge research presentation. We're going to also release some problem solving sessions some problem solving sessions that we recorded in the past for you just to work on them for the exam to get ready. Okay, thanks a lot and see you all tomorrow.